Hello class, this is Dr. Anderson, and I want to give you some background on your basal metabolic rate and temperature in preparing for class. When we think about metabolism and we think about our metabolic rate, ATP should come to mind. You may have learned in previous classes that ATP is the currency of the cell, and what the heck does that mean? Well, it's ATP is how you pay for things. If you want to pump an ion, you have to pay for that. You have to phosphorylate the ATPase and move the ion against its gradient. ATP is a beautiful energy source. So you have an adenosine and 3 phosphates, and between the second and third phosphate, that's called a gamma bond. It's got a beautiful amount of energy, just the right form, just the right amount. Beautiful for driving cellular reactions. And when you think about all the reactions you have, there are sometimes those reactions involve transferring energy from one molecule to another, or storing energy in a bond, or breaking a bond and releasing that energy. So a lot of times chemical reactions we can think of as an energy transfer. And we have to recall the laws of thermodynamics, that there is no such thing as a perfect energy conversion, that if you take ATP and you phosphorylate the sodium-potassium ATPase so you can move sodium against its gradient, some of that energy pumps the ion, but some of it is lost as heat. And when you break down an ATP to fuel the power stroke, some of the energy in ATP moves the myosin head so you can slide the cross bridges, but some of the energy is given off as heat. So think of things we're using ATP for. We've talked about the cross bridge cycling for muscle contraction, for pumping ions against the gradient, for making peptide bonds, for moving organelles around in a cell. Anytime you synthesize something, calcium ATPases, hydrogen ATPases, so lots of things in the cell are using ATP. So all of the reactions in the body, forming bonds, breaking bonds, all of the reactions in the body are what we would call metabolism. Every time you have a reaction, heat is liberated. So if metabolism are your reactions, and when you have reactions you release heat, you ought to be able to measure heat and get a measure of metabolism, and you indeed can do that. We can do something called direct calorimetry and measure heat. The unit that we measure heat with is the kilocalorie, or calorie with a capital C. A kilocalorie is the amount of heat required to raise the temperature of a kilogram of water from 14.5 to 15.5 degrees centigrade. So direct calorimetry is a measure of heat. So essentially what you have is an isolated room with a pipe that flows through the chamber, and that pipe carries water. And if there's a person in the chamber giving off heat because of their metabolism, you measure the temperature of the water as it goes through the room, the beginning of the room, as it leaves the room, the heat that's been taken up into the water then are the kilocalories of metabolism. You don't find rooms like that every day. There's a lot of temperature research that goes on up at the University of Minnesota in Duluth, so they have a chamber like that to measure metabolism. As far as I know, we don't have one at the University of Minnesota. And it's not really practical for clinical settings either. So in clinical settings at the University of Minnesota in Twin Cities, we use indirect calorimetry. The thing is, if you are assuming that most of your metabolism is aerobic, then you can measure oxygen consumption as an indirect measure of your calorimetry. And you use a spirometer. Person breathes in and out of a device. The device has the ability to remove CO2, and as the volume is removed from the device, that tells you how you're removing oxygen. So that's indirect calorimetry. You can get that from a ventilator. You can get that at the bedside and calculate someone's metabolism. You also can approximate someone's metabolism with their thyroid hormone levels. Now, this is a little bit circular, though. If someone has high thyroid hormone, that means they would have a high metabolism. You wouldn't really get a measure of the metabolism. You could ascertain if someone has a high metabolism or a low metabolism based on our thyroid hormone secretion. And admittedly, it's a lot more complicated than that. And later on in the semester, we'll be talking about thyroid hormone. So BMR is your basal metabolic rate. It's the basic requirement of cells so that you can stay alive. It's the basal amount of metabolism that you do. In order to measure basal metabolic rate, you measure it first thing in the morning after a good night's sleep. No food, no stress. So it's hard to measure BMR because, particularly if you come to class, you come to your lab, and you're going to measure your BMR. Well, you've probably eaten something. You've probably been running around. You've had some coffee. Those situations would not be. You'd measure metabolic rate, but not your basal metabolic rate. If you want to compare two people, compare somebody who's 6 foot to someone who's 5 foot, and say, which person has the higher metabolism? Well, bigger people, because there are more cells, are going to have a higher metabolism, but that doesn't necessarily mean that the smaller person has a low metabolism. So it turns out that metabolism is highly correlated to body surface area. So you measure metabolism, you normalize it by body surface area, and then you can compare two people and indeed say person A has a higher metabolism than person B. This has been shown in the animal kingdom. You could compare an elephant and a mouse. The elephant, if you capture the heat or measure a VO2, they're going to have a higher metabolism. But if you normalize the data by body surface area, you might find that a mouse actually has a higher metabolic rate than does an elephant. I think you get the idea. So what kind of things influence your metabolic rate? Eating, especially eating protein. When you eat, that's called a diet-induced thermogenesis. Interestingly enough, there seems to be a circadian rhythm with diet-induced thermogenesis, that the greatest increase of metabolism occurs when you eat earlier in the day. When you eat later at night, you have less of a diet-induced thermogenesis. This is where some of the dogma comes from that you should have breakfast, that breakfast is the most important meal of the day. Certainly, you should think about eating during daylight hours. There's some interesting data emerging about comparing when people eat. Actually, there's a very old classical study done. They recruited a bunch of people and had them eat one meal a day, one meal of 2,000 calories. Some of the subjects ate 2,000 calories in the morning. Some people ate 2,000 calories in the evening. The people that ate in the morning lost weight. The people that ate in the evening, then gained weight. So there seemed to be this this business of a circadian rhythm in terms of metabolism. Okay. Other influences on metabolic rate. Age. As you get older, your metabolism goes down. So there are databases where you look at what's the average metabolism of someone who's a child, someone who's in their teenage years, someone who's in their 20s. Because metabolism tends to go down as we age. It gets harder and harder to lose weight. It's harder and harder to fight gaining weight, those sorts of things. All sorts of neurosecretory influences on metabolic rate. Sympathetic stimulation is going to increase your metabolism. Thyroid hormone increases your metabolism. Growth hormone increases your metabolism. Those types of things. Body temperature. If someone has a fever or they have a high body temperature, then their metabolism will go up. If you cool somebody and bring their body temperature down, that will decrease their metabolism. Now, what if you maintain your body temperature, but you're in differing environments? There's a certain range of temperatures. Typically, the temperatures we live in our house, those are called thermoneutral temperatures, and you don't really have to change your metabolism to deal with that. But when you go into colder and colder and colder environments, then you have to work to maintain your body temperature, and that increases your metabolism. So could somebody hang out in the cold and lose weight? Theoretically, yeah. There was a Japanese study where they took people and exposed them to an hour of cold every day, and indeed they increased their metabolism and were able to lose some weight. If the environment temperature goes up, it also up above the thermoneutral range, it does increase your metabolism, but we are much less tolerant to really high temperatures than we are to lower temperatures. Metabolic rate changes as you sleep. When you sleep, your metabolism goes down. So someone might ask, okay, so if I get less sleep or if I stay up at night, will I burn more calories and lose weight? Well, some people have done this study, and it turns out, actually, no, you don't lose weight, because when you stay awake at night, you end up eating more. So if you want to lose weight, get a good night's sleep. Now, this graph shows you our x-axis is time of day, and the y-axis is your core temperature, which we typically measure by rectal temperature. And you see there is a circadian rhythm of temperature. So temperature is very low, about 4 o'clock in the morning, highest about 4 o'clock in the afternoon. So there's a rhythm in temperature, and we think about core temperature versus peripheral temperature. The core is in your torso, in your head, the vital organs, the brain and the heart and the lungs, etc. And the core is maintained by negative feedback and is fairly stable. The peripheral temperature is going to be more variable, depending on what you're doing to maintain homeostasis. If you are sweating and venting a lot of heat, your core might be kind of cool. If you are your skin could feel kind of cold and clammy. If you are really, really vasoconstricting, your periphery your hands could be ice cold, but while you're maintaining your core. Normal range of a core temperature is between 36 Celsius and 37.5. So when we talk about thermoregulation, there are a couple of things. We can vary heat production, because remember, heat comes from cellular reactions. So the heat that you produce basically is based on your basal metabolic rate. Then if you exercise and move around, if you're active, you you will produce more heat. Thyroid hormone, epinephrine, sympathetic stimulation increases cellular reactions and heat production. If your body temperature goes up, as with a fever, your heat production goes up. As you age, your heat production is going to go down. We can also talk about saving heat or losing heat. So we have the circulatory system that participates in our thermoregulation. If you vasoconstrict blood vessels in the skin that are called arteriovenous anastomoses, and those are regulated by sympathetic stimulation. When you constrict them, you keep blood in the core. If you don't have sympathetic stimulation and you dilate the anastomoses, then you have warm blood going to the skin. When you get the heat to the skin, then you can radiate it to the environment. How big of a person you are and how old of a person you are has an influence on some of these things. Babies have a very high surface area to volume ratio. So sometimes the rule of thumb is when you're comfortable, when you are comfortable with surroundings, dress your baby that way, but then add one more layer. Some of us have insulation, subcutaneous fat. So people that are obese or have a lot of extra fat tissue can be very, very uncomfortable in warm temperatures because it's very, very difficult to vent the fat or vent the heat because of the fat. I've talked about the arteriovenous anastomoses, and of course we promote heat loss through sweating, but it's very, very important that the sweat be able to evaporate. So in a place like Arizona where it's very hot but the air is dry, we're producing sweat. The sweat is evaporating because water has a very high thermal inertia. It takes a lot of energy to get liquid water to vapor water. Evaporative cooling can bring a lot of heat away from the body. So sweat needs to evaporate to cool you. Sweat that is dripping off of you does not cool you. So it is harder for sweating to help you lose heat in a humid environment. So here's a number of ways that we can transfer heat. Shoot, I was going to try to find my laser pointer, but I'm having trouble getting it to do that. Oh, here we are. So radiation is simply heat radiating infrared radiation. So the sun radiates heat, and that might warm you up. When you touch an object that's warmer than you, so she's touching the warm bath water, that heat is then conducted to her. Air currents move heat or coolness around. That can transfer heat. So radiation, convection, conduction are all two-way, but evaporation is only one way. You can only lose heat through evaporation. So when we regulate temperature, we're using a reflex arc. Remember, there are receptors in the skin. We talked about that under the neurophysiology system. We have both warmth and cold receptors in the skin that respond to a different set of temperatures. We have some visceral receptors that measure temperature, so in the deep veins and that sort of thing. In addition to the receptors in the skin. So warmth or cold would depolarize those receptors. They would send action potentials through afferents, both somatic and visceral afferents. That information is sent to the hypothalamus, which is the control center for temperature regulation. That information is also sent to the cortex so that you know about what the temperature of something is. In the hypothalamus is a control center. and a set point if the set point, well, if your body temperature is less than the set point or greater than the set point, then the control center is going to ascertain that you're too cold or you're too warm. Then a reflex response is going to occur through efferents. Some of those are somatic, so somatic efferents would perhaps go to the skeletal muscle so that you would shiver. Some would go to the adrenal medulla, so you release epinephrine. Those would be autonomic efferents. So effectors, we've talked about skeletal muscle for shivering, sweat glands for evaporative cooling, blood vessels for either saving heat in the core or sending warm blood to the skin to radiate away, and the adrenal medulla for the production of epinephrine. So this is a picture from Vander. The hypothalamus is the control center, but information is also sent to the cerebral cortex so that you know about it. We have our skin temperature. Peripheral thermoreceptors tend to act by feed forward. So you go into a cold environment and you immediately start shivering, or you go into a warm environment and you start sweating. You may exhibit those behaviors before your core temperature changes. Core temperature tends to be regulated by negative feedback. If your core temperature goes down, you're going to do something to get it up. And you have central thermoreceptors in the hypothalamus, along the spinal cord, and the deep veins that operate by negative feedback. So this is going to be the input pathway, the control center, and then we have an outward pathway. So sympathetics stimulate the adrenal medulla, and we get epinephrine. Epinephrine goes to the fat tissue, and in particular, a kind of fat we call brown fat. For a while, we thought only babies had brown fat. In brown fat, the lipolysis is uncoupled from ATP production, and you burn hydrolyze lipids in order to generate heat. Turns out adults do have brown fat. People who are thinner tend to have more brown fat. People who live in colder climates tend to have more brown fat. Sweat glands are going to lead to evaporative cooling. So that is an effector. The skin arterioles are effectors. You can save blood and warm blood in the core to reduce heat loss, or send warm blood to the skin to promote heat loss. And then there are a couple of things. An involuntary somatic innervation of the skeletal muscles causing shivering. And then the cerebral cortex can tell us to do all sorts of things. We could turn on a fan, or turn up the heat, or put on a sweater, or jump in place, or rub our arms and legs, or those kinds of things. There are all kinds of voluntary things we do. Please note that when somebody is under anesthesia, they can't do voluntary things to respond to temperature situations. They also will not be able to shiver. Now, if someone's operating on you, you don't want to be moving around and shivering. So that's why you're counting on your healthcare professionals to help keep you warm, wrapping you up in a blanket, heating the table that you're lying on, warming up IV fluids to body temperature. And then there are devices in the OR that can be used to keep people warm. When people are kept warm, they're less stressed and they're less likely to get an infection. Fever is another aspect of temperature regulation. So when people have an infection or exposed to some kind of invader, there's a response from the immune system. And we will secrete substances, interleukin-1, interleukin-6. There's some other pyrogens, tissue necrosis factor. Those will go to the hypothalamus and change the set point so that the set point is higher. So your body's going to say, okay, I'm 37 degrees, but my set point says I should be at 38. I'm cold. And the person's going to shiver, and they're going to vasoconstrict. They're going to get pale. They're going to curl up, and they're going to put on 14 blankets, and they're going to say, oh my gosh, I'm so cold. And they're going to shiver. So they'll reduce heat loss, increase heat production. And then the temperature goes up, and you feel their forehead, and you think, holy mackerel, they have got a really terrible temperature. Their hands might feel really, really cold. Now, they get better, the temperature breaks. What does that mean? The temperature set point goes back to where it should be. So the temperature set point is 37, but your body's been at 38. Now you feel hot, and you sweat, and you throw off the covers, and you try to reduce your heat production and try to increase your heat loss. So fever is a nice application of feedback. Now, when people have a low-grade fever, that could be a good thing. That might help your immune system be able to fight the invader a little better. You can do phagocytosis better. You can fight those little microbes better. Little bacteria need certain cofactors, magnesium and copper and things like that. If you heat up the body, then the bacteria would have to find more stuff to grow, and then they have a harder time surviving. So a low-grade fever can be a beneficial thing. If you have a really high fever, of course you want to treat that. Other thing is to realize is that older folks may not have a fever. So they might have a bladder infection, and they might need to be on an antibiotic, but they wouldn't have a fever. Maybe they'll get disoriented or appear like they have dementia. That's them trying to tell you that they have an infection, and they're unable to produce a fever in response to that. Of course, we talk about temperature regulation and anesthesia. So when people are in the operating room, there's an opportunity to get cold. You've opened up their body and opened up their chest or their abdomen, and heat is lost. They may be lying on a cold table, or the OR may be kind of cold. So you need to do things to help your patients keep warm. That they'll feel more comfortable, they'll be less stressed, they'll fight infection better. So, though on occasion people do get hypothermia in the OR, so people will vasoconstrict, trying to save heat. Their metabolism will go down. We're worried about severe hypothermia because that can cause dysrhythmias. If the blood gets colder, it's harder to coagulate. You have decreased respiratory rate, decreased cerebral blood flow, decreased GFR. However, with cold, it's harder for the nephrons to reabsorb things. So even though the filtration has gone down, you're not reabsorbing water and salt, and people will have a diuresis that causes your hematocrit to go up a little bit through dilution. So you want to prevent people getting cold when they wake up from anesthesia and they shiver. It is really uncomfortable. People just feel terrible. They'd almost rather be in pain than do that terrible shivering. So keeping people warm, warming IV fluids up to body temperature is a helpful thing, using those bear hugger devices and those kinds of things to keep people warm. It is easier to keep people warm than to try to warm them up after they've become hypothermic. Other thing is, when your body temperature goes down and you have a decreased GFR, you have a reduced clearance of drugs. And so you have to think about drug metabolites and how drugs are being used. The dysrhythmia is really big issue. Decreased coagulation, really big issue to think about when providing anesthesia. So this is the end of the presentation. We will talk more in class, and Dr. Olson has an idea for a little critical thinking exercise we can discuss in class as well. Thanks for listening, and I will see you in class.